I'm Kieran, and essentially I work for the Smith Institute, and generally this is going to be a talk of two halves. The first half is going to be what types of problems have I worked on, and the second half is going to be for a given problem, what do we do or how do we approach it so that our solution can somehow be used in practice. So someone, whether that be the public, a company, whatever, can gain value from it, and it's not just a prototype or a proof of concept. So if I scroll down, first half then, because most of the time I go to events, no one's heard of us, or someone's like, I've met person X and that's it. So what do? Well, broadly, we are a team of mathematicians, statisticians, data scientists, physicists, who tackle difficult problems, whatever difficult means, across a range of industries. So we won a Queen's Award for our work in telecom spectrum auctions, where essentially we're validating very large optimization problems. We have been nominated for 3 Data IQ Awards, which are all related to the practical use of an AI solution we developed for the electricity system operator, or National Grid, essentially. And also we are one of the UK's Groby partners. But beyond that, we sort of work in a few distinct areas. Energy is a big one nowadays. That's what I spend about half my time on, I would say. And then security and defense, which obviously we can't talk much about. FMCG, so lots of companies that make things that have short shelf lives. How do you optimize all of that? Transport, so this is sort of asset management, asset degradation. When is it safe to do things? When do I need to make interventions? And then broadly, spectrum and space. So it's a bit of a variety, but the same type of problems come up. And essentially, this is sort of the company goal or ambition, is some sort of positive and visible impact. And I think the visible part is what interests me particularly, in that average people, I would hope, are somehow benefited by a lot of the projects we do, as well as obviously the environment nowadays, and there's a lot of focus on that. But beyond that, so for sort of a few broad areas of what do we actually do. So intelligent decisions, essentially, a lot of the things we do are decision support tools. People need to make decisions, they have many options, what should I pick? And some things as well relate to just deeper insights. So a common sort of consulting problem is, here's a data set, I want to know why X is happening, or I want to understand what drives Y in this data set. And generally, because a lot of our work is in optimization, there is a big aspect of operational efficiency. So lots of people have enormous optimization problems. They've simplified them down by some degree so that you can actually solve them with maybe hardware or software that was written, I don't know, in the 80s or 90s. And nowadays, things have scaled up. You can imagine renewables in the grid, for example. And those old tools don't really carry over, so you somehow need to improve them and rephrase the optimization problem. But skipping on slightly, so the type of questions we get asked broadly for each of those applications, broadly things like, we keep getting it wrong, what should we do? And sometimes this is when the problem isn't even well posed. They just know what they're doing isn't right, but they don't know what they should be doing. What is going to happen? So this is sort of prediction in general, but perhaps prediction of some complex system where there's multiple parts going on. And as well, we know a lot of people nowadays, of course, come to us and say, we have heard about the emergence of AI or whatnot, and is this something that we should be using, and what could we use it for, things like that. But I would say it's really, every problem is bespoke. We don't really do off-the-shelf problems we don't do problems with off-the-shelf solutions. And then I think this is the final who are we slide. But so this is a quote from one of the customers we work for. I'm not allowed to say who, but essentially a lot of what we do is sort of reassurance. You've got a model now, or an optimization solver, or some analysis, and it's backed with some rigorous mathematics behind it, and essentially a big aspect is reassurance. So on to the main part of the talk. Three examples of what we do. So on the left is, so we have a project with EDF Energy, who run various power stations in the UK, and they have to make safety cases every so often such that this is to some degree of risk and it operates safely. So how do you actually model that? So that's sort of essentially all uncertainty quantification. This second one, managing uncertainty of supply and demand forecast. So essentially National Grid, ESO, keep the lights on, and you can't get that wrong. If you have a grid that's imbalanced, you have serious issues. So you hold some spare capacity, or what they call reserve, essentially generators that can move up or down if you have a shortfall or an excess in generation. But the problem is every megawatt of reserve you hold costs you money, so you want to hold the smallest amount possible, but every megawatt that you don't hold gives you some element of risk. You could, in theory, fall short. So how do you balance this monetary aspect, because they have to balance the grid at a certain risk level with minimal cost, but also balance against this risk when the risk is perhaps very hard to model. And this is the project that was nominated for the Data IQ Awards earlier on. And then there's essentially a few different activities, all in spectrum auctions. So I have some amount of spectrum. This auction might enter into the billions of dollars in sort of magnitude. So if I get this solution wrong by 1%, in relative amounts it's not a lot, but in absolute amounts it becomes significant. And you could open yourself up to all sorts of liability if you get it wrong. Three others, so sort of optimization relating to satellites. So this was positioning for some objective function. And then we have sort of a more data sciencey or data analysis one. So Coca-Cola, or Euro Pacific Partners essentially, can you understand the impact the weather has on the demand for their products? And therefore, when you've understood that, how do you optimize where you're stocking things? And then for a unnamed UK rail company, sort of building their internal data science capabilities with them so that they can then progress onto using sort of more modern techniques in their modeling. Okay, so now the rest of this talk is essentially for a given problem, whatever of those six or beyond, how do we make sure that what we do is actually used in production and doesn't just become a prototype that a report's written about that no one ever benefits from in practice? So a key obstacle we see that prevents AI or any form of automation that could be an optimization solver, let's say, from actually being used is, well, essentially it breaks down into lots of different components. I think this was not the slide I expected. There we go, problems. A few of them relate to essentially skills gaps. We can build the most complicated, beautiful AI system in the world that has minimal prediction error, but ultimately if you hand that over to someone and they don't fundamentally trust it or understand how to maintain it and things like that, then it just becomes some legacy software that goes to die. A big one that I'm interested in, mostly from the sort of academic sense, is trust in AI or explainability in AI. So there are various ways to generate explanations from an AI system. Do people understand what those explanations mean and how to interpret them? And of n possible methods to generate explanations, which is the right one? And then we have this sort of culture and understanding. I think there's a lot of hype around AI from a lot of people we speak to, but it's more just everybody's talking about it, not so much I have a specific problem that I know I can solve and it's sufficiently non-linear that AI might be useful. And then seeing through the hype, ChatGPT is everywhere now, right? A lot of people even use that. But a lot of the problems people face are sort of more mathematical in nature, and then AI is one of many tools you can use to tackle that. And should I be using AI, or should I be using Bayesian statistics because there's so much uncertainty, or should I be using something else? And then I'm sure everybody is fully aware that data quality is wildly varying, even between time periods of the same organization. So can I even train and use on the same data sets and same quality of them? And then sort of compute infrastructure. So very few people have GPU farms, but equally sometimes you're running on, I don't know, the internal processing of a car, let's say. And what does that mean versus running on how you control the entire UK energy grid? So the sort of process we've developed, and this does always evolve, but essentially to try and make sure that what we're doing goes into some sort of ongoing benefit and doesn't just sit as a proof of concept forever, is to, before we even start doing anything, have some sort of preparation, workshops, things like that, and say, what problem do you have? And is that even a problem you should tackle with AI, or is it a problem you should tackle with something else? There's hundreds of years of mathematics, statistics, and physics before AI, and it's not all irrelevant now that we've got nonlinear models that you can train. And then sort of designing solutions that we know end-to-end are going to run, before we start building anything. And that solution could include what sort of visualization and outputs you want, so dashboards, things like that, but also what are your data pipelines going to look like, what do they plug into, do you actually have real-time access to all this data, as well as an actual model that predicts something. And then essentially when all that's agreed, we sort of build a model, but we also build the end-to-end pipelines and outputs, deliver that in some way. Perhaps we host it, perhaps we hand it over to the customer, and perhaps we integrate it into their systems, or perhaps they do it. And then often ongoing partnerships so that people internal to the teams we're working with are upskilled. So we don't just give people a black box and say, hopefully that works for the next 20 years. And then it's sort of a bit more specific on issues we come across. So one of the fundamental things that comes up is, do people understand sort of the overall challenge, or do they hear hype about AI and want to use AI for something? So perhaps we could call that understanding the macro challenge. But a large part of this, in sort of part one of this partnership, is saying, what actually are you trying to do? Are you trying to address a symptom of some wider challenge, or are you actually trying to solve the problem at its source? And so you could say, I want better forecasts of demand, but why do you want that? Is it because your costs of balancing are too high, and is that subject to something else, like you're not selecting units efficiently? And there are plenty of rabbit holes you can go into in data science in general, that when you're looking at a complex system that has several hundred components, narrowing down exactly the right ones to look at is part of like an ongoing expert judgment kind of thing, I think, where a lot of the insight we take is from people, but then phrase what they're saying mathematically and then saying, okay, address X, Y, Z. And for our predictions or models or optimizations, whatever what we're doing does, what actually are the inputs that are feasible to use in real time, and how are these things currently solved? So more often than not, there are rules of thumb that work all right in practice, and people want to move away from those. But can we justifiably, and to some level of risk, move away from those and actually have something that's better? You know, it's quite hard to beat 50 years of experience of someone doing something every day. And how do humans fit in? So very, very rarely are we completely removing a human from the problem. A lot of the times it's decision support for a human expert to look at. And then limitations versus practicality. So you could probably get a great mean square error metric if you train a model for 10 days on a GPU farm, but practically, do you really want to do that? Very rarely is the answer yes in any of the problems we come across. So then on to sort of problem formulation. There are lots of industries or problems we work in where there's so many aspects to a system, the full problem formulation is so complex you can't really get a handle on it. And it's also not, this team's department to look at the entire thing. They're just focused on one particular thing, national demand forecasts, or the Coca-Cola product specifically in each country or whatever. And we can sort of ask ourselves, well, okay, what potential scenarios might come up in the future that we should be robust to in these sorts of things? So a different element of the system changes, so the demand forecast we were getting fed as an input suddenly shift, for better or for worse. For worse because there's a national COVID outbreak, and for better because they improve their models or something. And who exactly are the stakeholders here? Is it just the team we're working with, or is someone above them actually going to benefit from this? Beyond that, so architecture nowadays matters a lot more because compute power is a bigger aspect of AI than it used to be. But essentially, we have two broad options. Someone comes to us and say, we want improved X. And we say, okay, we can just take what you've got, get rid of it and start from fresh. Or we can take a specific part of your large system and improve that. So replace your current rule of thumb with some robust model. And how often should we do A or B? Well, the risk of doing A is enormous, but maybe the benefit's much better. Whereas B, you have to make sure that whatever you're doing is going to slot into everything else. So there are various limitations. For example, if we make a model, it has to predict at a certain time resolution because that feeds into something else down the pipeline that isn't going to change for the next 50 years. Now that imposes some constraints on your model, but practically it's probably a lot more useful to do that than it is to just say we're going to completely start from scratch and you've got to change everything. And essentially, yeah, we're always striving to build stuff that works and will continue to work, not just tear everything up and say, wow, you have to change everything at once. And methods before requirements. So this is something that I often bang on about if you've ever been to a talk of mine. But there was a time during my PhD where there was just papers coming out all over the place, and it was essentially neural network applied to X. People were applying it to predict whatever. And this thankfully hasn't fully carried over into industry, but because there is so much hype, and when people think of AI and machine learning, I think the general public think about neural networks. So they might say, oh yeah, we want to use machine learning. In their words, they probably mean neural networks to do something. But in practice, it's sort of crazy to say beforehand, use a method before you understand your problem, right? Because, well, firstly, is it even a data science problem? Well, okay, data science problem is perhaps too broad. Is it even a machine learning problem? Can you get 80% of the performance with a linear model, which already has explanations with it? Also, if your data pipelines are subject to lots of uncertainty, should you just use a Bayesian model? If you have industry experts that have worked there for 50 years, there's a lot of knowledge you're throwing away. Now, physics-informed machine learning is getting larger too. Physics has existed a lot longer than machine learning has. And do we want to completely throw away all these laws we know about and say, oh, let's go fully data-driven and rediscover them? Probably not. So one thing I always say is we should never go into a problem saying, oh, yes, this is a classic AI problem. We should instead say, what do they really want? And then what do we want to use as a function of that? And sometimes, yeah, going to companies and saying, yeah, this isn't an AI problem. We can solve it with a linear problem. We don't need any new compute requirements or anything is shocking, but it's a positive thing to simplify things. And obviously, with that, we can say things about your data quality, your compute power. And ideally, I say the take-home message here is, if anybody comes up to me with a methodology before a problem, I sort of say, stop, let's swap this around and think about it. So data overload. Sometimes we are in the situation where we have very little data and have to come up with a model. Other times, we have enormous amounts of data, many distinct sets, many distinct types of data, and there's an assumption that take them all, do something magical, right? And can we actually use all of those things in real time? You can develop a proof of concept with a historical dump with, 1 million Twitter messages, with real-time forecasts from the Met, whatever. And then you could say, well, in real time, we're not so confident those forecasts are going to represent the same levels of error and whatnot. Oh, and this other data has been sense-checked and verified afterwards, so that's a bit better quality. And all of a sudden, our prototype has wildly different error metrics to the production. And that's purely because we were, in the ideal world, super idealistic, and then we faced reality later on. So before we do anything as well, data overload. So what is actually available in real time? What can we process fast enough? What has been edited afterwards to create this proof of concept or this first pass that isn't reflective of what's going to be used in practice? And is this data actually repeatable? So if we just call the same prediction model twice, will it give us the same output? Now, if you're doing things like MLOps and one of the inputs to our model is some prediction elsewhere, if they retrain that model and it starts fundamentally drifting or whatnot, we can't be confident that that input is even sensible to use. And yeah, are we talking about historic dumps? Are we talking live data feeds? If it's a live data feed, how long is it going to be up for? I know the data source I use for my PhD no longer exists, and that was only 3 years ago I finished. And obviously there's a huge amount of cleaning and processing. If I need minute-to-minute predictions, can I process the data sufficiently fast in real time to do that? And some people call this a data audit or plan. I think it's essentially just think about real-time usage before you think about creating a model to prove that you can do something. And then error metrics. So I give you n models, and I say, the mean square error of this one's the best, right? So we should pick it. Well, almost certainly not in practical scenarios, okay? Partly because you can always improve an error metric, but perhaps as you do that, you get a less explainable model, you get a slower model, you get a model that requires more compute power. But also, there's some larger process here, right? So if a human is using my model to do something, the optimal model really is the one that helps that person the best. Now, that might have the lowest error, but also it's probably the most interpretable. It's probably the one that quantifies uncertainty. It's probably the one that's most robust to X, Y, Z, which might happen. So error metrics in sort of academia, right? You fit various models. You say, here's the state of the art. My error is lower to some confidence. Great, I publish a paper. In industry, things are fundamentally different, I think, and this is not really appreciated as you go from one to the other. And yeah, what exactly does a good model look like? Well, it depends who's using it for what and when. And then explainability. So, machine learning models in general, a long time ago, lots of criticisms. Black boxes, we can't trust them. 2017, unified explainability frameworks started to come out, so things like SHAP values and whatnot. And since then, there's still been some progression, but it's not, in my opinion, yet at the point where we have a unified, justified, mathematically rigorous approach to explain the outputs from an arbitrary black box model. Certainly not under all possible model types and under all possible data types. Now, with that, even if I give you explanations, so feature attributions, my change is X because feature took value Y, do people understand and trust those explanations? Not always. And is it enough to take some post hoc feature attribution method and say, oh, my model's no longer black box because I'm giving you these explanations? And it depends really on the application as well as the uncertainty, because a lot of these machine learning explainability methods don't give you a quantification on the uncertainty of your explanation. So to summarize, essentially, we want stuff we do to actually have a shelf life, to be useful, to be practically relevant, and not just be a proof of concept that we write a report about and no one uses. So to do this, there's sort of all the steps I've talked about, but broadly I think it's a lot of these problems are fundamental maths challenges or statistics or data science or whatnot. And there's a lot more to data science and sort of applied modeling than just building a really good model. And appreciating everything outside of that is really the route to get to something that is practically useful. And we do have some successes of things being used. So, for example, the ESO project I talked about earlier, that is being implemented in ESO systems. So hopefully the grid is balanced better in terms of cost and risk because of some of these things we've been doing. But it is a sort of an ongoing battle. And I think that's it. But yeah, any questions, thoughts, comments?
Fantastic. Can we thank Kieran, please?
Mm-hmm.